Welcome back to part 3 in our multi-part series on general relativity. This one's going to be a doozy. So we're going to start with more transformations in vector spaces. Then we're going to talk about a common thing that we do in GR, which is performing calculations in curve space and then interpreting them in flat Minkowski space. So that's basically going from coordinate basis to orthonormal basis. So we'll cover the math to do that. We're going to cover world lines, which visualize paths through space-time and translating between different points on that line. We're going to get into the weeds of covariant derivatives and even have a tangential discussion on covariance versus contravariance. It's important to understand when watching this that the crux of it is that Ben is trying to establish a definition of the derivative that is consistent with our use of derivatives in classical physics. Enjoy.
Hopefully the white balance is fine.
Yeah, the white balance should be fine.
Yeah.
And my eyebrows
Oh,
have been trimmed.
Properly trimmed this time.
So we are ready.
Thank goodness.
Welcome back.
Hey, again. Always nice to be down at the anechoic chamber. I can hear myself think. It's one of the few times. So, last time, right? This is the third part in the series leading up to the prediction of gravitational waves because I found that really cool as a concept, right? Last time, this is all the stuff that we covered. I figured I'd put that on there for everyone to see. We went over kind of why vectors are important and how we can generalize those to 4D. We talked about the idea of a dual vector and things that eat regular vectors in order to output numbers. How those work, how the upstairs, downstairs notation kind of works. And then eventually we go, well, why did we limit ourselves to only eating one vector? Let's just have, any number of vectors that we care about, talking about tensors in general, and built from that kind of our understanding of how derivatives are related to vectors. And that lets us understand a more general concept of what a vector should be, even if you have a curved spacetime, because little straight lines don't always fit nicely when you have curves in how your space behaves. And from that, we were able to build the this guy here, our tangent space. And we made the comment about how the tangent space corresponds to flat spacetime, which is, as a running theme, flat space-time is what you and I and everyone experiences. Flat space-time is where we can interpret the results. And so understanding how everything happens in flat space-time is going to be an important thing. Now, here's an important point. And this is why actually introducing tensors is going to be useful. Let's get into it. Is that in order to look at events on the curved space-time that I had and then interpret that in a flat space-time, I'm going to have to look at how does something happening on the curved space-time look in the locally flat space-time, right? And mathematically, what that is going to be a change of basis. You change basis from the basis you have on your curved space-time and you change it into the basis of this flat space-time. Well, how the heck are we going to do that? Well, we're going to find out that this is where tensors start to be really useful. These objects that eat vectors and give us real numbers are going to allow us to make the links between these different spaces. So let's imagine, right? I've got a curved space-time that I'm interested in, right? And we'll call this manifold, this thing, we'll call it just the space in. And I'm curious, how will it look if a vector from somewhere else acts on it? So this would be, let's say, my flat space-time, and I've got a curved space-time with different coordinates, m. Right. So this guy, m, is going to have coordinates x upstairs, mu, and the n is going to have coordinates y, alpha. And the question is, okay, how will a vector that's over in this space look acting on the flat spacetime? How will I be able to interpret it? Well, with the way this works, I can define a map. which I'll call phi. Okay. And that map will take the vectors that I see here into an appropriate vector over here, which so I would call it, say, phi acting on v from m gives me some vector, v prime in the flat space-time that I'm interested in.
Okay, so we're translating from x to y. And just a reminder that x is not like x-axis. This is a multi-dimensional vector.
Yep. So this would be the x, y, z, t as m sees it versus the, x, y, z, t as y sees it, as n sees it, right? So these are two spaces which have different coordinate systems, right? And it doesn't have to be broken up into, x, y, z. It could be that, say, m is in Cartesian coordinates, but n is in polar coordinates, spherical polar coordinates for 3D space, right? What x and y represent are just how you keep track of what a point in space is, right? Where a point in space is relative to whatever origin you define, right? And in physics, we're allowed to pick whatever origin we want for each space, right? That's why I can talk about, ground floor being this floor in the basement, but also ground floor being the floor 10 feet above me when I'm interested in doing physics on the first floor, right, of a house. The place where we set our origin doesn't change anything about physics. So I don't have to worry about where I set. I just know that all the math will work out, that it's fine. Okay. So what we're interested in is, what is this phi? What is the thing?
You can come down a little bit.
I'm already way too excited.
Yeah, I know.
Look, I jumped into this and I'm like, we're going to do abstract math diagrams. I'm super excited. So the question is, how are we going to figure out what is this phi? Okay. Now, if you recall from, I think we did this in first semester quantum mechanics. Whenever you have something that involves derivatives, which, if you recall from the last lecture, vectors are little bits of derivatives, right? A vector A can be thought of as its components and little differentials that tell me the direction, the coordinate basis for whatever space I'm in, right? And those little differentials, those are actual derivatives. So what I would do is, whenever I'm trying to figure out how does a object that involves derivatives behaves in general, as I transform between spaces, what I have to do is I have to introduce a arbitrary test function that I haven't specified that I can have that vector act on. And then the idea is that I'll expand out, my math, and hopefully I will have something acting on f just by itself equals some other thing acting on f by itself, and then I can divide out that test function. So as long as that form shows, that means that it doesn't matter what the test function actually is, because I can say, the relation holds regardless of what it is, even though the function might represent something like, okay, if you're traveling, if your vector is, your 4 space, right? I can say from that the function could map what is the energy that you have right now, right? But if I say, okay, the test function is the energy, there might be a case that a symmetry that I find or a formula for a transformation that I find only works for the energy function and not for, say, the momentum function or the speed function.
Okay,
right?
So if I'm understanding this correctly, you're saying that the phi function is not universal for all possible operations that would be performed.
So what I want to do is I want to make sure that it is. So I don't specify the function. So basically I'm going to say something like, v acting phi v acting on f is going to be equal to some other thing g that I don't know also acting on f. And then I'll say, okay, the coordinate transform, maybe some g and then acting on v as well. I can say, from here I can divide out this vf and say phi must equal this g, whatever g is that I happen to be. It might be, the vector components squared all added up, or it might be just the components directly saying, okay, you just put the components directly in. The point being, whatever this is, this will let me figure out what is the thing that maps from M over to N. It lets me figure out what is this phi. Okay?
Okay.
So, diagrammatically, what this is going to look like when I introduce a test function, the idea is that this is a function that will map from N into the real numbers. So f takes some point in N, or even a vector in N. Yeah, it will take a vector in N and map it to a real number, right? So this is a dual vector, basically.
Okay, so it's like an operator,
Right?
Quantum mechanics.
Mhm.
Okay.
Technically, your vectors are going to be your operators, and so operating on this function gives you a thing. But
I see.
yeah. You know,
Okay.
what that means is, I will make an assumption here. I will assume here I've defined that phi takes me in this direction. I'll assume that my spaces are compatible enough that I can define an inverse equation. Okay, so I can talk about phi inverse, which would pull the function back onto, right, the function that takes stuff from N, and I can have it, no, now it'll take functions from M.
So there's constraints on these spaces, like M or N can't be a black hole or something like that, right?
Yeah, certainly.
Okay.
Well, the next, we'll see how we kind of deal with Schwarzchild geometries. Basically, you kind of ignore everything outside of an area when you are making solutions to what we'll eventually find it's the Einstein equation based on curvatures, and that's what GR is all about. It's going to be a fun thing. But yeah. Yeah, because and setting up this picture is important, okay? Because what it lets me do is say, okay, I can figure out how V will look in M on this test function F via two routes. I can say, okay, send V into N by hitting it with phi, and then acting on the test function. So here, recall, since V is a vector, it's going to have components V alpha and what I will abbreviate as dou alpha. Basically, I'm just going to say dou alpha is simply that, right? Just partial differentiation with respect to that direction in that coordinate system.
Okay.
So this will have components, phi acting on the components alpha and in the direction phi, or in the direction alpha, and that all acts on the test function f, right? Equivalently, I could say, okay, let's take this test function and send it back into M, which would be this phi inverse acting on f, which will be acted on by V mu dou mu. Well, let me give myself some more space. Sorry.
You have lots of it.
I have so much space. I should use it, right? So the vector in M looks like this, and that acts on the pulled back function f minus 1, or phi minus 1 of M, phi inverse of M. But I know there's an operation that lets me do these inverse operations right away. Specifically, I can just do a composition. F of phi, right? You do this in, gosh, I think just basic algebra, which is just saying.
What's that doohickey between F and phi?
This is the composition operator.
Okay.
Right. If I have, let's really pull it back here. If I have a function, say x squared, and I have another function x plus 1, then I would say that f composed with g is I put g into everywhere I see x in the original function. So this would be x plus 1 squared, right? This is notation that you should be familiar with, but it's not that hard to understand. Basically, whenever I see a composition, when I'm looking at derivatives, what I should be thinking of is chain rule, right? And so chain rule tells me, oh, right, v mu, I just leave alone. And what I know is, okay, I look at, chain rule tells me I take the derivative of the function in its own original space, which is the alpha, right? The alpha coordinates. And then I take the derivative of the function that it takes variable. So like real quick, right? Basically, this lets me say that, phi lets me say that, I believe I'm having this correct, that a point's coordinate system, if I'm mapping it from M into N, should be phi acting on x mu, right, alpha. So the chain rule of that is basically saying, oh, okay, this function, I can just take the derivative of that coordinate system alpha with respect to the original coordinates that it's a function of, right? This is like saying that if I want to know what is the derivative of this, I take the derivative of f in its own space, let's say x, and then I take the derivative of g with respect to, well, like y, right? If
Your G's look like Y's.
they really do. It's so bad. I'm being too
There you go.
flippant with how I'm writing. That's all. So what this lets me do, I now have everything that I kind of need, is say, oh, okay, this, right, since it's being summed out, doesn't matter necessarily where it is. So I can say that phi, which to balance things out will be a function of alpha and mu, is simply that partial derivative of coordinates alpha differentiated with respect to coordinates on mu. So if I want to change bases and see, what do I want to say? See, like, how does something look from one space to another? All I have to do is compare the coordinates of the space that I'm traveling to, that I want to look at, see the vector here, and I want to see how it looks in this one. So I'm traveling to this space. I take its coordinates and I differentiate those with respect to the original coordinates of the vector that of the vector space that I'm starting with. Okay.
Okay.
So this lets me transform from any set of coordinates to any other set of coordinates.
Okay, so this is the generic approach to determining phi.
Mm-hmm.
Okay.
Right. So no matter what type of space you want, you end up with this type of object that depends on all the partial differentiations of all the coordinates of your new space differentiated with respect to all the coordinates of the old space. So, right, since we're looking in GR, we're looking at two 4D spaces. Your phi would be a tensor, that's a matrix that's 4x4, right? Similar to what the metric is, right? And when you're transforming, basically, like the way that I would actually perform the algebra is the same way, but it plays a different role.
Okay. Just so we're understanding the notation of this right here, this phi upper alpha lower mu.
Mm-hmm.
Okay. Is this the phi that goes from x mu to y alpha?
Correct.
Okay.
So what I've discovered is that phi should depend not only on the alpha components of the original space, but it also will depend on the components that I'm transforming to. So if I want to know what does the new X space look like, well, it's going to depend on the old Y, X, and Z, and T, right? It'll depend, the way, one component, one coordinate will look like will depend on all four, potentially, of the old components, right, of the old space.
Okay.
old
Now,
basis vectors.
So with the inverse of this, you would flip the alpha and mu?
Basically.
Okay.
Yep. And so since these are going to be nice manifolds, they get, in spacetime we assume everything's nice and smooth. That is a condition called Hausdorff for math heads out there, which basically just means there's not tears and everything in there.
Black holes.
Hence we stay away from black holes.
Yeah.
It's fine.
Right.
Right. If you have that, then you can do this, right? In the same way, often physicists will just, you can invert your differentiate. If I know, if I want to transform back and forth between spaces, I literally just take the two differentials and I swap them, right? Now, the idea of a differentiation acting like a multiplicative inverse will drive any real mathematician crazy. But you can prove that that's basically what it boils down to.
Yeah.
Through things. It is so surprising. But if you look at the basic formula for the inverse derivative in even just like Calc 1 that they teach you, it makes sense that it happens to work out that way in Euclidean space. And in nice, smooth manifolds, it doesn't take much more work to generalize it. But yeah.
Yeah. Well, I mean, especially if you're thinking from a linear algebra standpoint, right? You would just expect phi to just be a matrix to go from one space to another.
Mm-hmm. Well, I mean, that is what phi is.
Right. Like, but done using just traditional linear algebra.
Yeah, where you have to like find it out.
Yeah.
Yeah. Well, I mean, that's the nice thing of working with the idea of manifolds is that because of the math, like on a higher general level, you're able to piece together kind of what things should look like using notions that are outside the lower level. So like this should work even for any general matrix, like when you do a transformation.
Right.
But the reason that it works out like that is because of just this general idea. And in fact, like, I guess I'll spoil some of the next lecture here. This idea of looking for behaviors that are more general, more symmetric, and lessons that you learn from there and bringing it down and saying, oh, because of these, it must be this way, even though the math on this lower level doesn't directly tell me it must be that way, lets you simplify the math that you have to work with on this level rather significantly. Once we get to, in a couple of lectures, I will go over solving the Schwarzchild geometry, basically the stuff that leads to black holes, which is going to be really cool. But the way that you do that, and it's one of the first things that popped up because it's one of the most symmetric boundary conditions, like initial conditions for these types of geometries, which makes it one of the easier ones to solve and actually get an analytical result. And that's all because of the symmetries that you introduce and say, okay, assuming we have a space that has all of these symmetries, the math simplifies. And then bam, I can actually get your result.
Right.
Anyways, yeah. So this is the tensor that takes us from one coordinate system to another. Our little functional guy here, phi, which again is going to be useful because, like I said, you are often going to be changing back and forth between coordinate bases and orthonormal bases. And basically that's just, I'm going to be looking at just the general spacetime and flat spacetime. So the distinction really easily. So coordinate bases.
And just so we're being clear, because we're switching back and forth between curved spaces to spaces where everything is at right angles. All the basis vectors are at right angles.
So yes, here, real quick. I'm showing you here.
Oh, okay.
Right. A coordinate basis is something that when I look at the dot product of at a point in space time, right? Dotted with another one. So basically I'm making my metric at a particular point in space time. It just gives me any old metric that depends on those two indices for whatever the bases were, right? This is your general metric. But if I have what we call an orthonormal, which, as you said, is
Just to recap,
metric is the thing that lets us define distances in our space. It's the thing that lets us define a length between 2 points, and from there we can build areas, volumes, four volumes. Here, and I should say, these are the little vectorial quantities. Here, I give these guys a little hat to specialize that they are, to signify that they are the orthonormal bases. And their product together gives me eta at that point, which is the diagonal matrix that just has -1, 1, 1, 1, right? And zeros everywhere else. So the 4x4, where along the diagonals, it's these four numbers and 0 everywhere else.
And you call that Minkowski space?
Yes, that's Minkowski space. That's flat space-time. That's where special relativity takes place. That is the stuff that we we experience, we feel like locally. Everything makes sense there. It's all happy. It's when you get onto these larger, big spaces that you have to be like, I got to go into coordinate space. So the important point here is that when I'm making calculations, the easiest way mathematically to do it is to look at how do things behave in the coordinate basis. But then when I want to interpret my results, I look at what is the flat space-time, what is the orthonormal basis, what does it look like in the orthonormal basis at that point. So, basically the idea is go to this picture here, you do all your calculations bouncing back and forth between points on the, there we go. On the curve itself. Why are you like this? Stupid iPad. But I want to transform any event into the tangent space at that point in order to interpret and understand what the heck is going on. Yeah. So we'll go ahead and go down.
Or if you want to make your math incredibly complicated, you just stay in Minkowski space the whole time.
Well, I'm not even sure if that's quite possible. And in fact,
okay,
we'll get there. Actually, phi, what will often represent this as also being, actually, I should say, as being equal to, or, yes, this is going to be E mu in alpha space, right? If I want to transform something that's like, say, a tensor from what it would look like in just regular space, say like T alpha beta, and I want to know how is it going to look in some flat space-time, hence the little hats to indicate this, and this is the only time I think we'll really deal with this, but I would look at, okay.
And you're calling that a hat over beta?
Mm-hmm.
Okay.
Alpha. And E hat, E vector beta. Right, so I take it from the coordinate basis at that point, and then I say, well, okay, also there's a tangent space, so I can lift it up into that via basically this formula here.
Is there a hat over the alpha next to the E and over the beta?
Yeah, there's a little hat here, and there's a little hat here.
These are all hats.
Yes.
Realize not a single one of your hats looks the same.
I'm trying to write too fast.
Yeah.
I am trying to write too fast. I should probably slow down with this.
Yeah, you can slow down a little.
I just always feel so slow when I'm doing this, which, yeah, probably.
Well, you've rehearsed it. Everybody else watching it might be seeing it for the first time.
Bad habit. I've thought of it in my head, and I'm just like, oh, yeah, of course. I should just try and get through this information as quickly as possible.
Okay.
I don't know. That's a very bad lecture habit. It's fine. I'll break myself of it eventually. Eventually, you'll yell at me enough that I'll be like, oh, yes, I shouldn't do that. I should at least plan on how to do this properly. Let's make that parentheses nice and better. All right. Now, so that's as far as we'll get with coordinate transforms. And that's an important thing to understand. Another thing that's that we're informed about, right? Because this whole little bit started about how do we take the vectors that were so useful in classical physics systems, regular Newtonian physics, E&M, statistical mechanics. How do we elevate that to this new 4D space and now, allowing for curves, and like how does this differential geometry picture work? Another thing that's going to be really quickly when looking at the lessons from those fields is that an important quantity is probably going to be understanding how do vectors change, right? So basically, it would be nice to differentiate a vector quantity in this space, right? Because you think about Maxwell's equations, and that is entirely based off of the differential properties of the fields, right? You look at what is the gradient, not gradient, you got curl, and I can't remember the other one.
I was going to say curl, but
you got curl because that's del cross, and then what's del dot? Divergence. It's the divergence. Divergence and the curl, because those are very important things, and those are the differential operators acting on those fields, and that gives you all of E and M. So it might be very important to understand, if I've got a vector here, how does that vector evolve in time? Now, you have to think from here, how do I attach, how do I think about how does one vector evolve into the next? Well, how do I, if I've got this entire field, what do I say, this entire space that could be filled with vectors, what do I say this vector is somehow attached to that vector? The very natural thing that I would guess at would be, okay, I'm going to attach vectors based on the world lines that I talked about before, right? So if I want to see how does a particle travel throughout space-time, I would follow the fundamental object that I'm going to be creating and paying attention to is this world line, right? This guy that kind of sweeps through and is, x alpha that's parameterized by something sigma. What we'll often do is say, oh, okay, this guy is parameterized by his own space-time, or by his own, not space-time, his own proper time, right? Basically, the time that he would measure from here to here,
right?
In his own frame of reference, right? Now, I would be interested in, oh, okay, how does the vector that he follows along here, the vector along this curve, how does that change as you follow this world line? So how does this vector that's tangent to his world here evolve as it goes from, say, this point to this point, right? As I can clearly see, there should be some relation based on the trajectory, the world line that we build, that this vector and this vector should be related somehow.
Insofar as they're both tangent lines.
Right. Okay. Insofar as they're both tangent lines to the world line that we defined, right?
At two particular t's.
Right. So an important point about something here, and this is actually a thing that important. This is something we will call U. It is a 4 velocity. And if I go, and this is the 4 velocity that you would see in special relativity as well, like you look at your proper velocity.
So this is Cartesian and time.
Mm-hmm. Okay. It could be. Obviously, I could change my basis, and it doesn't necessarily have to be Cartesian. But yes, right. But this is the thing that takes in all 4 time and space dimensions that you're working with, right? A consequence of how we define this guy, right, basically being, I believe it is going to be your gamma factor, right? If you remember, you go back to the very first lecture on just special relativity, we said that gamma was this 1 over square root 1 minus v squared over c squared, where v was your velocity in just space, like so your 3 velocity is what they call it. This is how we define our 4 velocity. So it's just the gamma factor in time and times gamma vector times your 3 velocity. A consequence of this is when I dot this guy with itself, I get a -1, which means that this thing always has magnitude 1.
Okay.
Right.
Now, is this something you could just do with the simple Galilean equations for position, velocity, and acceleration? Or is it going to be more complicated because of that gamma?
It's more complicated because of the gamma. It's that
Okay.
Lorentz, right? You can't quite do this in just regular old Euclidean space. But the fact that how we've defined our 4 velocity is the whole reason that any of the math for differential geometry works in general relativity, actually.
Okay.
Here's a fun, a fun bit. You can run into things that like invalidate your theorems from just general differential geometry if your curves have velocities that have magnitude greater than 1.
Okay.
This is fun. So basically, you just always have to make sure that you scale your space so that it works out this way, which is what we've done here. And a fun little math fact.
Cool.
Isn't it weird? Now, here's very quickly a problem, right? Like when I think about differentiating a vector, right? Or when I think about differentiating anything, what I think about is taking the idea of some function and looking at, oh, okay, over some distance, it's going to run a little bit and it's going to rise a little bit. That we learn in just algebra. And then introducing the calculus idea of bringing this distance, some horizontal distance h, and I want to bring that down close enough as possible to 0, like sufficiently close to possible. But in practice, these 2 points, this point and this point, are always going to be at different points in space, right? Different points along your x coordinate. And what I would want to do is look at different points along my spacetime, right? Because obviously if I'm looking at just the same point, the vector isn't going to change. But here's the trouble. The picture that I defined before, where we had our tangent space where vectors live and everything's all nice and dandy, is only defined for 1 point in spacetime. And there's no reason that I could, as far as what we defined so far, relate this tangent space to this tangent
Oh, yeah,
space
they could
over
be
here.
completely different.
Exactly.
Right.
Right? So the question is, how do I go about trying to rectify this problem?
I thought that's what phi would do for us, though. So phi does not give us that.
Phi is not, because it's not quite the same thing. Because while I can so because of how these guys are related, right? Because they're defined as this projection map, there's not a strong connection between these 2 tangent space. What you would have to do is go through phi, like through the underlying manifold itself. Because the underlying manifold itself, I would somehow have to transport across that. Because phi basically tells me, how do I go from the curved space to this? But like, how does the point on the manifold that is shared between, the coordinate system of the manifold and the coordinate system of the tangent space itself? Phi lets me say, oh, okay, these 2, touch at a single point. I can transform between the basis here and the basis here. And I can do the same thing for this guy, for, the space over here. What phi doesn't tell me how to do is how to transport between 2 separate points.
Okay.
What it lets me do is say, okay, if I've got some event here that's shared between 2 spaces, I can say how it looks in one basis versus another. But those bases have to coincide at some point. But here, these guys don't coincide the right way. If I extended them out infinitely large, they would correspond in this, potentially very complex.
Okay. So we haven't fully defined a function that actually provides that mapping between the two different
Right.
points on the world line.
Right.
Okay.
Right. The way that
But then once we get there, we can use phi.
As will be, nice. Right. So yeah. So like if the whole idea is that as is written out in different stuff is that, you take a limit of that ratio. So I've got f at some point plus a little bit later, and then I subtract from it f at that point, and then I let the distance divide by that little separation, and I, do the limit operation to bring it down to zero, arbitrarily close to zero. So for a differentiation, I need to have subtraction, and in order to do that, subtraction is only defined within the space that I have, right? So subtraction between vectors is only defined within the tangent space that those vectors should live in. So I have to come up with some way of, if I want to compare two different vectors in different tangent space, of bringing one of those, the vectors from one of those tangent space into the other one, right? So that they overlay the proper way. So here's the way that we go about that. It is a thing that is called parallel transport. So let's say I've got an arbitrary vector that's attached to a world line x alpha. Okay, so x alpha is at this point here. Right, gotta use 2 fingers for that. X alpha is at this point here, and there is some vector, points off, say, in this direction. Let's give it a bit more of a tilt. Something like this. So this is the vector at that point, x alpha. And the world line is such that if I zoom in enough, the world line looks like it moves in a straight line to this point here. Some straight line amount, what I'll call dx alpha. Very, very small distance. I've just zoomed it up a lot for emphasis. And so this point would be x alpha plus that little bit that I've moved, dx alpha. Right? And at this point, the vector looks something like this. Let's make it a little bit shorter just for emphasis, right? So this is the vector at x alpha plus dx alpha. Parallel transport lets us just say, oh, okay, I can talk about this vector being parallel transported. So I change nothing about how it's angled or anything. I just say, okay, it is this corresponding vector in the appropriate tangent space that is v parallel transported back to x alpha. Okay. And now, since these guys basically originate from the same point, I can have some notion of the difference in my vector, right? It is this idea of parallel transport that's the key notion of defining derivatives on vectors, because it what lets me bring the vectors from some other space into the original one that I want to know how it differentiates. So, if the distance dx alpha happens to be oriented along some straight line defined by a straight vector t alpha by a little distance epsilon.
No correlation to time.
No. This is just like when right in the last lecture we said, oh, you could look at dx, the differentiation of your world line with respect to its proper time. That'll just call a vector t to the alpha. But in t, there is potentially a time coordinate. It just depends on what value you select for, alpha. Anyways, so what I can say is that the differentiation, what I will define as a covariant derivative in the t direction of my vector v at a particular point in space-time. Now, to be proper, I should have little arrows over all of these guys. That will be the limit as I let my epsilon tend towards 0 of the vector v at that little distance a little bit far away, t alpha epsilon, parallel transported to x of alpha minus the original, what the vector looked like originally there, and then divided by epsilon.
Yes, you're basically just dropping the x component. So
what do you mean I'm dropping the x component?
Well, okay, so you're moved over a small differential of the original x, the x alpha.
Yeah.
Yeah, so you're basically you're just dropping that one little differential amount because you're limiting it down to 0.
Yes. Yeah. Yeah. So basically, right, like in the limit of calculus, what I would do is take this distance here and shrink it down,
Right,
to 0, so that I can arbitrarily get that. And so from that, I can build up the whole line as it changes from point to point, just in the same way with regular differentiation, right? If I know how the derivative behaves, I can say, oh, okay, it looks like a little straight line across this tiny infinitesimal distance. And then once I get to that point, I can look at how the straight line looks this way. And then here I can look. And then that eventually builds out the whole curve, right? So this is the covariant derivative. Right? So here's a fun little aside. The reason that we call it the covariant derivative is an interesting fact in how we let things transform. So let's say, real quick, that I have some vector, right? Some vector v, and it's defined in the xy coordinates. So I would have y, x, right? What I would have is that v, right, would be some v alpha e lower alpha, right? This should be the same thing regardless of if I change my coordinate system. So I could talk about E beta, where here, let's say, instead of Cartesian coordinate systems, now I've changed into some polar coordinate system. So I have a radial E, right? So this is E.
Oh, I didn't even see those blue lines.
In the radial?
I didn't even see the blue lines.
Oh, yeah, I just drew them now. Right, E in the radial direction, and then I would have...
Can you see that blue, Bills?
E in the phi.
Yeah, you can see the blue.
Okay, like that. Now, even though I've changed from xy over to radial components, notice how V, as I've written in this diagram, should not change at all. But if I look at the basis, I can talk about how the R...
I actually really cannot see the blue at all.
Oh, man. So basically, R points along this direction here. R points along this direction here.
Oh, my God, you put a smudge on the screen.
I know, I did. I'm a bad
Bills,
person.
bring the... It's in the...
Can I get the microfiber cloth? Because I'm a terrible person.
In the drawer, all the way in the back.
And then you define basically, circles that are at a certain radius around. And so phi at different points tangent to that. Here. It's fine.
I know. It's actually pretty visible. There you go.
There we go.
All right.
Right. Okay. So what you'll notice is that the basis has changed. So I could describe each of those basis vectors, say in the blue, as
I cannot see the blue. I really can't. Can you go to a different color?
can I change colors? Why not? Let's get rid of these.
Yeah.
It's a shame.
Well, the ink is very skinny. I don't know if you made or you're zoomed out, so it's not very thick.
It could be
There we go.
something like that.
Yeah, now it's visible. I
So
can
this
see
is
just fine.
terribly drawn, but that's fine. So I've got, a radial and here a theta component.
Okay.
E theta. And so notice like the red lines I would describe as a linear combination of the black vectors. Right? I would say, oh, okay, I can talk about, ER being x plus y directions divided by their magnitude, and then phi is I think it's like a inverse tangent of the two. But the vector itself hasn't changed, right? So the idea is that when we define these spaces, we want to make sure that regardless of how we change bases, the vector itself doesn't change. But if you look at how I've drawn this, right, the vector depends on the basis that it's being described in. So here's an interesting thing between dual vectors and their components. The bases are things that we say transform covariantly. They transform. They don't have to be an invariant. If I go from one coordinate system to another, they're allowed to look different, right? If I go from xy, the basis that I have, obviously, if I go from xy to some either rotation of that or polar coordinates, those basis vectors are going to look different. And I describe that, basically I just find and say, okay, these things transform covariantly. They if I want to describe one in terms of the other, it's going to be a appropriate ratio of all the old vectors that it works that way. The components of my vector, the V alpha, in order to preserve what the vector is, basically, so that regardless of which coordinate system I'm in, when if I transform from one coordinate system to another, if I transform from xy to polar, that the vector still describes the same thing. It has to transform in a way that is called contravariant.
Okay. So I thought that's what we were trying to describe with covariant. What is the difference between covariant and contravariant?
So basically, covariant will change. A covariant object will change based on how the basis vectors change. So when I look at how...
But use this as an example of, let's say I've got two magnets. All right, and I know in a perfectly flat space that when I let go of this thing, it's going to go right to the other one. It's going to track toward the other one. And so you're saying a covariant, if we were somehow changing the geometry of space, that I would actually observe it arcing to, or going off in a different direction and then ending up.
It's like saying if I look at different lab frames, right? If you and I are measuring based on, say you're doing XY and I'm doing polar coordinates
right.
as my thing, we won't agree on the basis that we're measuring because our basis vectors will be pointing in different ways. Right. I would describe,
right.
You would describe your basis vectors as 1, 0. I would describe mine as also 1, 0. But when we look at each other, they are in fact very different. But there are intrinsic properties about a vector, right? So the fact that when I let go of this magnet, it travels some distance. So let's say that distance is, we consider it a vector, right? Because it's gone some magnitude and it goes in some direction. Those properties should be invariant regardless of how you're describing them, right? The way you're looking at them,
right.
or the way that I'm looking at them.
Correct.
So there's a difference between how the way that we measure things transforms versus the things that we are measuring transforms.
Right.
And so the way that we measure things transform will be what we call covariant. And because and it's simply a fact of they don't have as much restriction on what they can be, basically. They are allowed to change as a linear combination of the old things. But say, for example, the length of that vector, that length has to stay the same regardless of whether you look at it or whether I look at it. And that direction also, right? Even though I would describe the direction differently based on our different variables.
And that's covariant, what you just described.
Yeah. So covariant is where things are allowed to change. Contravariant is, no, I must transform it in a way that something remains preserved. The length stays the same, counter to any change you make in how you look at it.
Okay.
But that's...
Yeah, you're kind of losing me then, because isn't that covariant? Because wouldn't we measure the length of a vector to being the same length, even though we're in different coordinate systems?
Mm-hmm. No, that's simply... now what we're getting lost in is like just what the meanings were. So if I measure the length, like the vector has to have that same length, that means the vector transforms contravariantly. But the bases that I would describe that, how that vector breaks down, like the components of the vector, the bases that I would use to describe the different components are allowed to transform covariantly.
So is this kind of like the Heisenberg picture of quantum mechanics versus the Schrödinger picture, where in one the state vector changes but the basis remains the same, and in the other the state vector remains constant and you change the basis around it?
Yeah, that's kind of what I was asking. That's why I was like...
Get in the comments if I'm incorrect, but I don't think it quite maps that way. We're getting that. Yeah, I'm not quite sure about that analogy. Okay, no. So let's do it that way. So yeah, if you pick, gosh, I can't remember. The Heisenberg is the one where you allow your basis vectors to change, right?
Yeah, where the operators are time dependent, but not your state vector.
Right. It's been forever since I've actually done this stuff. Anyways, so in that picture, right, like the difference of the basis, I can allow them to do whatever they need. Like if I'm comparing where the operator basis gets me to here versus there, right, I can describe just straight up how the math says, oh, okay, this thing looks at this finger here looks in this space according to this particular thing.
Translating back
here,
and forth, right?
Right. But that doesn't have the same constraint that as I rotate these different things, this vector here that always stays the same regardless of how my hand moves, this guy has to transform in the view of my finger in a way that always makes sure that it's pointing in this direction and has this magnitude, right? Basically
pointing in this direction according to whom?
According to anyone. But that we would agree that, that flower is pointing towards the North Star, perhaps.
Okay.
Right. No matter whether I'm looking at it this way or whether I'm looking at it from down, but that direction to some other, that direction and magnitude is always the same.
Have we described anything in which that scenario would not be true, where this flower would actually pointing towards the south?
I mean, I'd have to say. Okay. So, let's say what you're comparing is, say, like the first basis vector, right? If I have my coordinate system like this, and let's say this is my very first basis, what I define as my x. When I transform to another basis, there's nothing saying that I can't have my first basis point in that direction. But if I have a vector in this space that looks like this, in this space, it has to also look like this. But there's not that same constraint on where I point this finger when I rotate it, right? The first basis vector can be pointed in any direction when I make that transform. But a vector from this space should always point in a way that I can agree on, whether I'm measuring it in this space or in that space. Right?
Right.
So I can measure x as this way or this way, but either space. So there's not a constraint on how these two fingers relate in order to have something that is invariant between this finger here and that finger there.
Oh, wait, okay. So you're saying
But whether I'm looking at how this flower points this way or in this basis, or whether I'm looking at how that flower points in this way, that flower has to have something invariant about it. Specifically, it's how tall it is and what direction it points in. The fact that it points towards the North Star.
okay. So let me see if I'm understanding what you're saying correctly. You're saying there's one base. I have two bases, right? Right, and both of them, this star or this flower always points towards the North Star.
Mm-hmm.
Period. Okay. Now, what you're saying is that there are multiple components of this basis. We're only talking about one.
Mhm.
All right. Let's just say it's the vertical one.
Mhm.
Right. You're saying is that the other basis vectors in this space, I might transform them in a way that here they're 90 degrees relationship. They might be like this in this space.
Yeah.
But we still have to,
Yes.
when I measure along this vertical,
When I measure that particular vector along the vertical, yes.
okay.
Right. Because in that instance, and perhaps I'm getting too in the weeds here, but in that instance, you happen to have one of your basis vectors aligning along the flower. But there's no constraint that a basis vector has to align along the flower.
Right.
So if I move it off there, that is a transform, that's fine. But regardless, I still have to see that flower pointing with that magnitude in that direction.
Right.
Right. Yeah. Fun tangents. Sorry for that, if that was a bit
Well,
off of what was like the easiest way to understand.
we'll see. We'll find out in a minute.
The important point is that we are going to, and this is why we want to define it as a covariant derivative, because the notion of what we'll use this derivative for will be in order to account for how coordinate systems transform as you move around. Basically, right? So really,
But covariant never changes the measured outcome.
no. Contravariant never changes.
Contravariant never changes the measured outcome.
Based on like say how the space transforms or anything, like how the space is shaped. But covariant does move along with it. Contra means opposite of the transform. Covariant means it will.
Okay. So
Moves along.
contravariant says that no matter which basis I'm measuring it in, that flower is always pointing up. Covariant says, no. We might actually disagree on the direction that flower is pointing.
Right.
Okay.
You and I will disagree on what the direction of the first basis vector is, but we will be able to deduce that the flower points towards the North Star.
In both covariant and contravariant?
In both of our coordinate systems. Our coordinate systems, to transform how my basis vector transforms to your first basis vector, that is a covariant transform. Basically, you're allowed to do whatever you want in simple terms. But the flower, when I look at it, how it transforms from my view to your view transforms contravariantly because it has to stay the same. There's a constraint in how it looks.
Okay.
In to both
So
our
both are
views.
happening at the same time?
Yeah.
Okay.
Yes. Which is exactly right here.
Okay.
I've got a covariant transform in the E here, but a contravariant transform in the components V alpha here.
Okay.
Sorry. Yes. So when you have a vector by the vector is just in the most abstract sense, just an arrow that's kind of out on its own. It exists. The way that I look at it when I define a basis is how I kind of pin it down and work with the math. But in order to make sure that it keeps that pure essence of everything is the way that it should be, I have to make sure that the two different types of components transform in a certain way.
Okay.
Yeah. A little mathy speak. But anyways, so what this most directly says is, okay, like here we did this before. I can talk about this being effectively a chain rule. So I can say that this thing, let me get back to white here. This thing is simply the differential of my world line with respect to the parameter it has, in this case, epsilon, and the partial derivative between the vector itself excuse me. I should do this differently. And x and beta. Basically, make sure that these sum up, and then I have the derivative of my vector in the alpha component space. And then since I've already got alpha taken up, I need to sum across a different coordinate system. And if I look at the differentiation on this guy, which we already discussed, I can talk about this being some vector t, right? The direction that this points along in this space, and say, okay, so this is some vector t times the partial differentiation of the vector alpha with respect to x beta. Now, this is what it will look like. If I drop the direction component, right? If I drop differentiating in a particular direction and just say, okay, what does the vector look like differentiating anything? That gives me a tensor. And that tensor is simply going to have components dou beta v alpha. And that's just simply, partial differentiation of v differentiated with respect to all the components that I could be interested. So, the different components of my vector, it's the vector component, the time direction x, y, and z, differentiated each of them with respect to the x, y, and z. Because, that component of the vector might change as a function of all of those components. Right? So there's nothing stopping me from, having, my vector be defined as something like x plus y in the time direction, t minus x in the x direction, right? So I have to account for that and do all the differentiations. So it's in 4 space, it's a 16 component thing, 4x4 matrix.
Okay, so this is decidedly non-Euclidean or non-orthonormal.
Yes.
Okay.
Well, I mean, here actually in flat space-time, this is fine. This works. But there is...
Yeah, but you don't have x depending on, or t depending on x plus y. Or sorry, you don't have x depending on y or anything like that in orthonormal space.
I could, because remember what we're doing is we're looking at a vector that's a function of some line, basically. And that line might be described by these functions. That's a perfectly fine thing. And you can do that even in Euclidean space.
Oh, I see.
Does that make sense?
Yeah. All right.
Because
you can pick any function and you're the one that determines that it's dependent, right?
That line, that world line, regardless of the space I'm drawing through, is how I attach different vectors and say, oh, this vector goes from here and becomes this vector over here in this other spot.
Okay.
And it's attached via this line, and that line is just parameterized by, basically how the components act as functions of the point in space-time that they are in.
Right.
It's a little complicated, I'm not going to lie.
Oh.
Okay. There is a problem, though, because we wanted to have, in order to make this all work, I needed parallel transport. But in order for parallel transport to be meaningful, the space and the representation of this vector here at this point, x plus dx distance, must exactly match the representation of it when I pull it back to this point in space-time.
That was too much pointing.
Okay. Oh yeah. Okay. Excuse me. When I want to take this vector and parallel transport it back to the original point here,
right?
I have to make sure that I do it in such a way that this guy and his parallel transported self match up. Okay?
Well, you just meaning they're just on the same spot in the world line.
Yes. Yeah, when I bring it back. But here's an important point, right? Let's say I've got my XY space. And let me just say I've got this vector here, X, and then I've got, this is X plus dx, a little bit over here. Let's say it's the same vector. I want to basically take this vector here and parallel transport them this way, right?
Mhm.
And so, I can agree that these two things are the same vector, at least as is appropriate to my crude drawing ability.
Right.
But what if instead of having xy, let's make it red. What if instead of having xy, I have polar coordinates, which is going to be, you have different radial lines, and then I make little circles, kind of like that. I'm so bad at drawing. It's fine. So the basis that I would describe at this point would point along this direction. So I would talk about, let me move this guy so he's here. Right? The basis that I would talk about would be here and here, because this is the E theta and this is ER, right? Pointing radially and along the theta direction.
Okay.
And so this vector in this space of components like this, right? So I have this length and this length as the two different components. So that's basically like a 45 degrees. So they're equally spaced between the two. Now, if I parallel transport to this point, again, my basis vector ER and the theta direction are these guys. And the components are going to be this distance and that distance. So notice, even though I'm in the same basis, right? As long as I don't change basis in Euclidean space, right? If I parallel transported these, the component of this vector, whether it's at x plus dx or whether it's x, those components don't change. And so from there I can say, oh, okay, since I haven't changed basis, I haven't done anything, I should, have the same component magnitudes in each of the appropriate directions. And that's how I know I've got the same vector, even though it's transported back to the same spot.
Right.
So if I don't change my coordinate when I parallel transport a vector, the way that I know that I still have the same vector is that its components in that direction are still the same, right? But, so like the component in the x direction matches the
right. But I mean,
both space.
that's obviously not going to be the case in polar.
Exactly.
Right.
So the easy formula of just saying, oh, okay, the partial differentiation is all I need for this covariant derivative falls apart even when I get out of rectilinear coordinates. And these are both polar and Euclidean, Cartesian coordinates are both flat spacetimes.
Simple systems, right.
They're both flat spacetimes. This is going to fall apart. This covariant derivative I'm trying to create is going to fall apart entirely when I try and go to curved spacetime. So how do we deal with that? Pretty simple. What we have to do is say, oh, okay, my parallel transport, right? Basically, the components V alpha that are parallel transported back to some x, and here I'll mark it with a delta, just so that I can keep track of the components of this guy as a function of the space-time point I'm at. Instead of looking at the whole vector, I'm looking at its components. Must be the components that I would get in flat space-time, basically. A little bit of transport, which in flat space-time, this is fine, right? This is exactly what we said. Okay, the components from one point in space-time to the next, flat space-time can parallel transport along a straight line, it's fine. If there's some changing in the angles that the basis vectors make as I move along space-time, that's the thing that changes how a vector looks in each component of my basis, right? It's not that the vector itself has changed, obviously, from the picture that I've drawn, right? I know the vector is the same thing. It's just that the angle it makes with a particular basis component has changed. And what that lets me know is say, oh, okay, it must be a function of just, well, the vector it is, its point in space-time, right? The vector that I see as a point in space-time. Here, it's the wrong index. Right, because obviously, depending on what the vector is, whether it's this vector or this vector that I'm parallel transporting, that's going to make an effect on the change in the angle that makes. It also depends on the direction that I'm parallel transporting it. So we'll call it dx, and this in beta. And it must be something that takes those two vectors and gives me, since on the left side I have a vector, it must be something that takes two vectors and gives me a vector, which we have.
I mean, that's pretty obvious, right?
Yeah, exactly.
Yeah.
But as we did last time, we have the thing that does that. It's a tensor. It's a tensor with two downstairs notations. It's beta, gamma, and an upstairs alpha. This is the component. So when I plug that into my basic form for the covariant derivative, what I'll ultimately find is that the covariant derivative, the tensor of the total derivative alpha, should be the partial differentiation I had before plus this tensor acting on my vector.
Okay. So you've got gamma there?
Yep, capital gamma.
Okay.
This is ultimately what we call a Christoffel symbol of the first kind.
Oh, I don't even mean the uppercase one. I mean the lowercase thing next to V.
Or
Or
okay.
the superscript of V.
Mm-hmm. Yeah. So I know I should end up with an index of alpha at the end. Everything should depend on delta. Yeah, the things that depend on delta should depend on delta, which would be both. Technically, this guy also depends on x delta. So I should have put that there, but whatever. I need to make sure that whatever
Okay, so those are all deltas, but we've got an alpha over there, and then we have a gamma over here.
Yeah.
All right.
A gamma, but a gamma
because
that is being
your
eaten.
doohickeys are very, very hard to follow.
Sorry.
Like, so is this an alpha here on the x, or is that a delta?
Alpha. This should be a delta.
Okay.
That is here. Here, we'll do this. Bam.
All right.
Solving everything by using the better Greek letter anyways. Okay. So this thing needs to eat the vector and needs to eat the displacement that I've done. So I choose two different indices that aren't the alpha because I know the alpha index should be what's left over because that's the only index on the left-hand side.
Okay, now that you've put lambdas there, how do we need to change the next line?
We don't. This is fine.
Okay. All right.
Yep.
I'll take your word for it.
This here is fine because the delta that I had before was explicitly talking about how it's a function of the space-time point you're at, right? Like, it's explicitly a function of this point here. Here, I've just suppressed that notation.
Okay.
It's implied that it is.
So basically what we're saying is when we're going from one basis to another, we have to take into account not only the two bases, but we also have to take into account the path taken to get from one to the other.
When I am looking at how does a derivative change based on some world line that I've defined.
Right.
So this isn't a change of basis, right? I have not changed my basis when I look at how this this derivative changes from here over to, some path to here.
Okay,
But what I have to
thought we
account
switched to
for-
polar.
Well, but like in both looking at this vector and that vector, I've stayed in polar coordinates.
Okay, so these are both polar.
Yes, these are both polar.
Okay.
And the trouble that we were having is that even though in both cases I was looking at them through polar coordinates, there was still a rotation. There was still like a change
Right.
in the the components. That the first component of this vector looked different here than it did there. That wouldn't be a problem if it were just a change of basis, because you're allowed to have the components look different. But since it's the same basis that I'm looking at this on, they should match if they're going to be the same vector.
Right.
And the trouble is in polar and in curved spacetime, right, that I don't get that. So to account for that, we introduce this gamma here, this capital gamma, that will allow for the component in the first vector to stay the same when I parallel transport it.
Okay.
So the last thing.
So it's basically a translation.
Yeah.
That maintains the orientation of the vector as it moves across the world line within the same basis.
Right.
Okay.
Yes. Yeah. Perfect.
Okay.
And so that way we are able to construct a consistent, comprehensive notion of a derivative of a vector. And we want that because we know it will be useful, because we have that information from just classical physics.
Right.
We have an intuition that it will be useful. So we're going to go through all this effort.
We do everything else using that.
Yeah.
Right.
So may as well it's a solid bit, and the next lecture will very much go into it.
Okay.
So here's a fun thing. Basically, from the way that we've defined this, I can say that a vector field is constant if and only if the covariant derivative function, goodness, my gadgets are bad, is 0 identically everywhere. Basically, just like I would say, like, a constant function is constant because its derivative is 0, right, everywhere along the line. A constant vector field should be 0, not in terms simply of the partial differentiations, but now because we're going to account for curvature, it should be the covariant derivative that is 0 everywhere. And that's what defines for us a constant vector field. Now, if the underlying space isn't curved, then you can just use partial differentiation. Everything's fine. So let's see. I wonder how long this derivation will take. Let's get at it. One thing, I think this will take another 10 to 20 minutes, and I don't think that's too much longer.
We're already about 120.
Are we at 120?
Yeah.
Okay, then I will just sketch out the basics. Two fun things. So I can use that notion. I can use that notion of saying that a vector field is constant if and only if the covariant derivative is 0 everywhere. And I know my basis vectors should be constant vector field, right? You've got little guys pointing each in that represent the cardinal directions that I'm paying attention to. I don't want those things to change. I don't want the meaning of them to change when I move it. So I want that to be a constant field. So what I can do is I can say, okay, the covariant derivative of the appropriate here, I'll have, I'll make it the dual basis vector. But again, vector and dual vector, and as far as general relativity is concerned, are the same thing. Or at least as far as this level that we're treating it at, are the same thing. And that will be equal to, obviously, the partial differentiation of that basis with respect to some space plus my Christoffel symbol of the second kind, eta gamma, E gamma. And what I want is that this thing should be 0, which lets me very quickly deduce that the partial differentiation of x beta is equal to the negative of the Christoffel symbol of the second kind, which is what this gamma with the 3, this tensor-like object is. So effectively, what this symbol tells me is how do my basis vectors change as I move along some coordinate system based on the coordinate system itself. So if I have, my polar coordinates and I know I'm moving from here to here, how does the, well, actually, if I have polar coordinates, it would look more like this.
Try it.
Yeah, you're right. I mean, that's exactly what we have here. If I have the polar coordinate system here, right, this is the radial direction and this is the theta direction, how will it change as I move, say, along this distance to here, right? And I know it'll be something like this. And what we'll find is that, and the thing that captures the transform is your Christoffel symbol. What we'll find is that this guy ultimately captures the underlying curvature of the space that we're working with, right? The fact that these theta lines are curved, right? So the angle they make with the r vector, and that the r vector, my radial vector changes as I move along. There's a inherent curvature to the way I'm describing my XY plane, right? Even though it's flat space-time, like the way I'm describing it kind of curves, right? I've got these curvy lines. But that Christoffel description generalizes even when I get beyond flat space-time and I actually have some crumply curvature. I'll skip over the derivation and I'll simply say that since in general relativity, what I typically have is that I am given, instead of my basis vectors and asked to deduce things, what I'm usually given is what is the, here is the metric at a point. Here's the metric across space-time. And so I want to have the Christoffel symbols defined in terms of my metric G, right? So it is a set of 3 partial differential equations. This is gamma plus here x beta minus EG gamma x delta. Yep. So no, the only alpha here is this guy. The rest, this is a delta, this is a delta, this is delta. So this is what the Christoffel symbol of the second kind looks like.
Are we subbed here? Beta, gamma? Is that a sub or is that?
Yeah, they're both. Right. Remember, the metric is going to be something with 2 lower indices.
But are they subbed here? And the middle one?
Yes.
Okay. All right.
Bad gamma. Anyways, so yeah, that ultimately is the object that will nicely capture what the curvature of your underlying space-time is going to be. And next time...
And that describes how the orientation of a vector translates as it moves along inside the same basis but along the world line.
And fundamentally, that lets us have an idea of what the curvature should be. Next time, we will go over how you can actually capture what curvature is in your space-time, how... yeah, and how, as far as the general relativity project, how that means we move through space.
Okay. Now, if we go back just a little bit, this is actually when we look at that del, when we're just dealing with simple things like E and M, that's the end of it. The del is just the partial parts without the
Correct.
Christoffel.
Yep.
Christoffel now generalizes this into any type of space that we could possibly describe.
Not any type of space, but any smoothly curved, right?
Correct.
We're assuming that our manifolds are, again, Hausdorff. They're smooth, they're well behaved, they don't have have cusps, they don't have anything that's
right. So, but this is basically
breaks
how
calculus.
we're going to extend that del symbol that we use so frequently in the fields to now work in general relativity.
Exactly.
Okay.
And we'll attach that to the things that physically matter, which boils down to F equals ma, really. And we'll show how that translates, and it's really fun.
Cool.
So yeah.
All right.
See that next time.